Okay, here's a neat trick you can do with velocity versus time graphs. Because velocity is measured in meters per second, which I'll write over here, meters per second, and time, which is down here, is measured in seconds. If I multiply those together, I'm just left with meters, the amount of displacement that took place. So if you think of it, if you multiply this value by this value, what it gives you is this area. So on a velocity versus time graph, the area under your line, or in some cases a curve, is going to be equal to the amount of displacement occurred, because meters per second times seconds leaves you with meters. So let's look at this first example. All right, first of all, we'll just answer the questions that come out. So what is the starting velocity? The starting velocity in this case was 30 meters per second. And the ending velocity was still 30 meters per second. Because if you look, there was no slope to this. So there was no acceleration that occurred. So since there was no acceleration, the slope is 0 meters per second squared. Now to calculate the displacement, all we have to do is multiply the y-axis, which is 30 meters per second. I'll do right here, 30 meters per second, and I'm going to multiply that by the y-axis, or the x-axis, which is 10 seconds. Now what happens there is the seconds cancel out, and what I'm left with is 300 meters, which is my answer here. 300 meters. Now look what happens in this next one. Let me just slide this a little bit. Now here we've got to use a little bit of, we got to remember a little bit about our math rules, which is that this triangle here, a right triangle like this, what happens is its area is equal to half the area of this rectangle here. Because if you think about it, if I drew this rectangle and cut it in half, and it's no accident that if you look at what I did, I made this have the same ending velocity. It too ends at 30 just like this one did, except this one, instead of starting at 30, this one starts at 0. So let's just try this. What is our starting velocity? It is 0. I'm not going to write the meters per second because it's just too messy. What is the ending velocity? If I look, the ending velocity is right here. It's 30 meters per second. So therefore, what is the acceleration? Now remember, on a velocity versus time is simply the slope of this line. The slope of this line on a velocity versus time graph is my acceleration, because the slope is this divided by that. So if I say 30 divided by 10, what I get is an acceleration of 3 meters per second squared. The displacement is going to equal, as always, as it was last time, it's going to equal the area under this triangle. Right? It's the area under this line, which is triangular in shape. So what I'm going to do is the way I'm going to get this is I'm going to say 30, which is what this is, 30 times 10, so I'm going to get this rectangle, and then I'm going to cut it in half. So it's going to be 1/2 of this area. So if you recall from before, the area of this rectangle, 30 by 10, is 300. So I'm going to say 300, but I'm going to divide it by 2 because I only have half of it. So the displacement is 150 meters. Let's try another one that gets a little bit trickier. If you see one on the AP test, it's likely to look like this here, where you've got to do a little bit more work. And that is, so here I started at 70. I'll just put 70 meters per second, but I'm not going to write the meters per second. My ending velocity in this case came down here to 20. I'll calculate the acceleration. The acceleration on a velocity versus time graph is the slope of the line, which is the change in y over the change in x. And if I look at the change in y, it's going to be the final minus the initial. So 20 minus 70 gives me negative 50. So I have negative 50 meters per second. And I'm going to divide that by 10 seconds. And that's going to give me negative 5 meters per second squared. Now for the displacement, here's what I'm going to do. I'm going to look at it. I'm looking for rectangles. Here's a rectangle right here. All right, it's the entire area under this. So what I want is this figure here. Is that trapezoid? All right. So what I'm going to do is I'm going to say, well, it's 20 times 10. Well, I know that's 200. So I have 200 meters there. And now what I'm going to do is I'm going to say, well, I've got another triangle here. It goes like this, all right? And I'm going to take half of that one because I just want this part of it here. So if this is 70 and this is 20, the difference is 50. So what I'm going to say is 50 times 10, because that's the time, equals 500. But because I don't have the full rectangle, I just have half of it. I'm going to divide that 500 by 2, which gives me 250 meters. So I'm just going to add those two together, and what I get is 450 meters. Let's go on to another one. Okay, here we have some negative values. And you just have to remember, negative displacement means that you're displacing in the opposite direction. Well, let's just start off answering the easy questions here. What is the starting velocity? That's 20 meters per second. What is the ending velocity? We ended up at negative 30. So that's a change of negative 50. So we went from 20 down to negative 30. So that's negative 50 divided by 10. That's going to be negative 5 meters per second squared. Hey, wait a second. Isn't that what we had on the one above? Yes, it is. If you notice, the one above was also negative 5. And although these graphs are slightly scale different, you'll notice that this, you'll notice that this slope and this slope are the same. It's just where they are relative to the zero velocity value. But now let's go on to the next thing. What is the displacement? So to find the displacement here is what I got to do. I want to find the area under this triangle and the area under this one, keeping in mind my positives and negatives. So this one is a displacement of 20, so velocity of 20 times 4. So 20 times 4, that's going to be 80, and I had to divide it by 2. So what I get for this one here, so this one here is going to equal 20 times 4 divided by 2, and that equals 40 meters. And then this one over here is going to equal, let's see, we're at 30, so 30 times 6, so it's going to be 30, negative 30, times 6 divided by 2, and that ends up being negative 90. And I'm just going to combine them. I'm going to say, well, first you displace yourself positive 40, say on the way up, and then you displace yourself negative 90 on the way down, and therefore the difference, if I just say 40 minus 90, what I get here is negative 50 meters. Well, I apologize for this question here, because it's not going to make a whole heck of a lot of sense, but let's just start. What is my starting velocity? Well, it was negative 20 meters per second. My ending velocity, well, it was, I went up, I went flat, that was, you know what, it was still negative 20. What was my acceleration? Well, my initial acceleration to start off with on this part here, I went from negative 20 to positive 20, that's 40, and it took 4 seconds. So that means for that part there, the acceleration was 10 meters per second squared. Then it was 0. Then I came the other way, and notice this is steeper than this. So when I calculate, I should get something that is has a larger magnitude than this in an opposite direction. So here, my ending velocity was 20, and my starting was positive 20. So that's negative 40 divided by 2 seconds. So that would be negative 20 meters per second squared. And then here, of course, I have 0. So I guess I really can't answer this one directly. I'll just have to do it that way. There isn't one acceleration. Now, what is the displacement? Oh boy. Well, let's see what we've got here. There's a trick I can show you that's pretty sweet. When you have a constant velocity like this, and if it starts at the same distance below the zero as it ends above it, they cancel out. So if you think about it, this area here and this area here are identical to each other. They have to be. And so therefore, I can just ignore those. They cancel each other out. This area here, whatever it is, and happens to be what? 20 times 2, 40, that's 20 and 20. Guess what? 20 and 20, negative 20 and positive 20 cancel each other out. Now what I have another area. I'm going to do this one in blue. I've got this one here. Look at that. It is 2 times 20, so this area here is 40. But I'm going to look over here. Look here, I have an area of 40 over here as well. So I can say, well, this 40 here and this negative 40 here, they cancel each other out. And you see where I'm going. Now look at this. Now what I've got. Hey, this one right here, which is basically, what, half of 20, so that's 10. That negative 10 is going to cancel out this positive 10. It all canceled out, and the displacement in this case was 0 meters. Who would have guessed? All right, we're going to move on to a different kind now. Now what we've got is if the acceleration versus time. So now we've got acceleration on this axis. So let's think about this. If you multiply acceleration times time, what does that give you? Well, acceleration is meters per second squared. And if I multiply that by seconds, what happens is this second cancels out one of those seconds. And you know what? Meters per second, that's velocity. So it's my change in velocity. So how much does my velocity change over the course of the time period shown? So, but I'm going to do the same thing. I'm going to use the area. So I'm going to say, all right, let's first do this. All right, what is the area of this part right here? Well, that's going to be 20 times 3. So that's positive 60. And let's just look at the positives first. So let's look at this area here. That's 3 times 10, so that's positive 30. So I have a total here then of positive 90 meters per second. And then, let's see, now I'm going to do it blue for the negative. So now I have 2 seconds times negative 10. That gives me, I'll just draw an arrow to it. That gives me negative 20. And here I have 2 times negative 20, and that'd be negative 40. So the total amount of negative change is negative 60. The total amount of positive change is positive 90. So the difference between them is going to be positive 30. So what happens is this person is going to end up going 30 meters per second faster than they started out. And so since this person started out at 0, according to this, it starts from rest, which is 0. If I add 30 to 0, I get 30 meters per second. So this has become a bumpy ride. Look at where you're speeding up at 20 meters per second, you're slowing down at 10, you're speeding up at 10, you're slowing down. It's like driving with Granny. Okay, now, if it depicts a car that started off at 25, what is the final velocity of the car? Well, the same thing. Basically, I'm just going to add 30 to whatever the start was. I'm adding 30 to 25. If I add 30 to 25, I get I get 55, don't I? So I get 55. And if I had added it to, say, negative 40, I would have gotten negative 10. So I'm gonna add 30 meters per second to whatever my start was. Let's try the next one. All right, the graph above depicts a change in motion in a rocket that had an initial velocity of, whoops, wrong thing here. Had an initial velocity of 30 meters per second. Let's keep that in mind. We want to know its ending velocity, so just find the area under the curve. So let's see, we have negative 30 times 6, and that's a rectangle, so I know how to cut it in half. So let's see, negative 30 times 6, that's negative 180 meters per second. And then over here I have another square. The nice thing about the acceleration ones is there's no There's no having to cut it in half. That's negative 20 times 2, so that's going to be negative 40. So the total amount of negative change is negative 220. And then how much positive change was? There's just a brief period of positive acceleration here, and that was, oh look here, I have positive 40. So I can just use that trick where I say, well wait a second, this one here cancels out this one here, so all I'm left with is this one here. So it's going to change by negative 180. Now if I start it off, it goes negative 180, so I start off at positive 30. So what I'm going to say is, well, I start off at positive 30, and I took away 180, and that leaves me with negative 150. So in other words, it's going the opposite direction at 150 meters per second. Now for your final kind of trick one. Well, it's not trick, it's just a little bit hard, and I can't draw it very well. I can't really use rulers on this iPad software I have here, but here's what we're going to do. Alright, let's look at, this is a great way of solving this type of problem. So a car started off at 60, so I'll use blue for the car. It started off at 60 right here, and it slowed down at negative 2 meters per second for 15 seconds. So I'm going to say is, well, how fast did it end up going? So I'm going to use V equals V naught plus AT to figure out the final velocity. So the starting velocity was 60 plus negative 2 times 15. So that's negative 30. So 60 plus negative 30 is 30. So he ends up here. I'm going to try to draw a line between them. I don't know how well I'll do. I didn't do that well. Okay, that line represents the car, starting at 60, ending at 30. Now let's look at the police officer. The police officer accelerates at positive 5. So let's use red for the police officer because he's angry at this driver. So he starts at 0, or she starts at 0, and ends up at 50, which is here. So now I'm going to draw a line from 0 to, and I'm going to stop when I get to the intersection. Okay, so what I need to do to answer this question, it says how far behind the car. So I'm looking for a distance between these two cars. So what I'm going to do is I'm first going to figure out what is the total displacement of the police officer. So what I have to do for the police officer is I have to figure out what is the area of this area under the police officer's line. Well, so what I've got here is I'm going to look at this point here. I'm going to call that 8.5. And I'm going to call this, oh, I drew this terribly. Alright, well, if I drew it correctly, alright, if you drew it correctly, because you can see how this line here kind of sags down. When I drew it correctly, what I found was that this point of intersection, I'll just tell you what my point of intersection on my correctly one drawn at home was. It had an x value of 8.5. and it had a y value of, I came up with about 42. And that's what I had. So what happened then is, if I say, well, this area here is going to be 42 times 8.5 divided by 2. So what I get is 42 times 8.5, 42 times 8.5. So, oops, I did it wrong. Okay, 42 times 8.5, and that gives me 375. But remember, 375 equals this area here, and I need half of that. So if I divide that by 2, so if I say, well, 375 divided by 2, the police officer, went a distance of 179 meters. So I'm going to write that in red underneath the police officer. I'm going to say, well, this area here is 179 meters. Now, if you think about it now, I can still use this because for the driver their distance is described by this total area here, the total area under that part of the line. Now, this part here we've already established is 375, and we just simply have to add to that the area described by this. Well, if this is 42 and this is 60, 60 minus 42, that's 18. So we have 18 meters per second times 8.5 seconds, which is this here. This is 8.5 seconds. All right, and let's see. So 8.5 times 18 is 153, but I have to divide that by 2 because I don't have the full rectangle. This rectangle here has an area of 153, but I only want half of that rectangle, so I'm going to divide that by 2. That gives me, let's just call it 77. All right, so the area here is equal to 77 meters, and the area down below, this total area here, is 375. So I'm going to add those two together. 375 plus 77 gives me 375 plus 77 is 452. So the car went 452 meters, while the police officer went 179. So I'm going to take the difference between them. I'm going to say 452 for the car minus 179 for the officer, minus 179 is 273 meters. That's how far behind the cars we are. Alright, so I'll try to get this published so you can look at it as soon as you get this assignment in your hands today in class.